Welcome to today's class. So in today's class, we are going to be talking about fluid mechanics. We'll basically start with the introduction of fluid mechanics and of course everything we need to know about fluid mechanics. Okay, fluid mechanics is actually the branch of engineering science which deals with the study of the properties of fluid at rest or in motion. Now, just like the name implies, mechanics, there are actually three aspects or three branches of fluid mechanics. We have the statics, we have the kinematics, and then we have the dynamics. Statics has to do with the aspect of fluid at rest. Kinematics has to do with the study of the motion of fluid, such as its velocity, its acceleration, without paying attention to the force causing that motion. Whereas dynamics has to do with the study of the motion of fluid, such as velocity and acceleration, while paying attention to the force causing the motion. Now, basically, fluid is simply, when we talk about fluid, we are simply talking about any substance which can flow or deform under the action of continuous shearing force. Okay, that's just what fluid is all about. And of course, in fluid mechanics, we have two branches or two types of fluid. We have two types of fluid. We have the real fluid and we have the ideal fluid. The ideal fluids are those fluids which do not have surface tension or viscosity. And of course, in real life, there is no such fluid that do not have surface tension or viscosity. Even water has a surface tension, but the surface tension of water is very small. Its viscosity is also very small, so it's purely unnoticeable. As such, we always consider water as an ideal fluid. But then there is no such fluid as an ideal fluid because every fluid has a little or at least a certain amount of surface tension or viscosity. But then real fluids are actually those fluids which actually have surface tension and viscosity. A good example could be your grease or your engine oils or any form of oil at all. So far there is friction in the flow part of the oil, we always call that a real fluid. Now, the basic things that actually governs the foundation of fluid mechanics, we've said that statics has to do with the study of fluid properties at rest. Okay, and the very first branch of fluid mechanics is actually statics, and that's where we're going to start our video. Okay, so in statics, what we'll study include density, surface tension, viscosity, specific gravity, specific weight, specific volume, and all that. So let's start with density. Let's start with density. Okay, as we all know, density is symbolized by the symbol rho, the Greek symbol rho, and it is simply defined as the mass of fluid flow within a given volume of the fluid. So mathematically, density is simply equal to mass all over volume. The unit is simply kilograms per meter cube. Okay, so density is simply the mass flow per unit volume of flow. Okay, also let's talk about specific gravity. Okay, simply S. All right, specific gravity is simply defined as the specific weight of every liquid divided by the specific weight of pure water. So mathematically, specific gravity S is simply specific weight. Okay, so I will use SP for specific. Okay, weight of liquid all over specific weight, okay, of water. All right, so this gives us a formula for specific gravity. Now, when they say specific weight simply means the weight of every substance divided by the volume of the liquid. The weight of every liquid divided by the volume of a liquid. That's what gives us the value of specific weight. So it's usually specific because it is usually in newtons per meter cube, simply weight divided by the volume of the fluid displaced. Now, for the aspect of fluid mechanics, the specific weight of pure water or simply specific weight of water is simply considered to be 9.81. Specific weight of water, okay, is simply equal to 9.81 kilonewtons per meter cube, and you can simply write this as 9810 newtons per meter cube. So this is a constant and it gives you, or it tells us, the specific weight of pure water always. So if the specific gravity of any liquid is known, we can always find the specific weight of that given liquid, knowing fully well that the specific weight of water remains 9.81 kilonewtons per meter cube. So I've talked about specific weight itself. Specific weight, okay. Specific weight, simply small w, it's simply the weight of every liquid divided by the volume displaced by the liquid. So it's simply weight all over volume, all over volume. And of course the unit is simply newtons per meter cube. So this gives us the specific weight of every liquid. So from the formula of specific gravity, if any liquid is given to you, and of course the specific gravity of that liquid is known, from this formula you can always find the specific weight of that given liquid. Okay. All right. So this remains the formula for specific weight. Now we can also obtain another formula for specific weight, knowing fully well that we obtain that density is mass all over volume. We know that density is simply mass all over volume. So which means from here we can make mass subject. If we make mass subject, mass m becomes equal to density times volume. I'll simply have density multiplying by volume. So this gives me the formula for mass. Now, what is the weight of every liquid? We have said that specific weight is simply weight of the liquid divided by the volume of the liquid. So therefore, what is now weight? Weight itself, we know, of course, weight W is simply mass times acceleration due to gravity. And we know the mass of this fluid now to simply be what? Density times volume. It means that the weight itself becomes density times volume times gravity. So if we have this to be the weight, that means we can also find specific weight from the formula. Specific weight of every liquid, simply WL is simply the weight of the liquid all over what? Volume. And we know the weight in this case. Weight is simply density times gravity times volume. We have density times gravity times volume all over volume. So volume cancels volume from here. This means that another formula for specific weight is actually what? Density times gravity. So keep this in mind. Unit remains newtons per meter cube. So we can always use this alternate equation to find the value of specific weight. If any liquid is given to you, the density of the liquid is known, and of course gravity is constant, 9.81, we can always find the specific weight of that liquid given what? This equation. Simply density multiplied by gravity gives us the specific weight of every liquid. Okay, having that in mind, let's talk about another parameter that governs hydrostatics, and that is simply specific volume. And that is simply specific volume. Okay, simply symbolized by small v. Specific volume of every liquid is defined as the volume of that liquid divided by the mass occupied by the liquid. Specific volume of every liquid is simply volume. Mathematically, it becomes volume all over the mass of the liquid, and of course the unit is simply meter cube per kilograms. And of course, if specific volume is volume all over mass, not forgetting that density is actually mass over volume, it means now that specific volume is simply what? The inverse of density. Of course, it becomes volume all over mass. Therefore, specific volume itself, specific volume can also be defined. Okay, small v is simply 1 all over density of the given liquid. So whenever a liquid is given to you and the density of that liquid is given to you, you can always find the specific volume of that liquid by simply taking the inverse of that density. That gives you the value of the specific volume of the liquid. Okay. So the idea of surface tension and viscosity, we're going to do with that later. Let's just consider these few ones we've stated here, and let's try to solve examples. Let's try to solve examples that pertain to these few we've stated. In the next video, we'll start considering surface tension, viscosity, and Newton's law of viscosity and all that. So we're going to consider from what we've learned so far with these formulas. Let's consider a problem and try to explain all the formulas from the problem. All right. All right. So to further explain what we've talked about in the previous explanations, let's consider the question on the board. It says, determine the mass density, specific volume, and specific weight of a liquid whose specific gravity is 0.85. So we are asked to find, first of all, density, also specific volume and specific weight. Now, we are given the specific gravity of this fluid to be simply 0.85. So X, specific gravity X, S is given as 0.85. So we have this. Now recall we said earlier that specific gravity S is simply the weight of every liquid, specific weight of every liquid all over the specific weight of pure water. And I said for the sake of calculation, specific weight of pure water is simply given as 9.81 kilonewtons per meter squared and per meter cube, per meter cube, and this can simply be written as 9.81. This can simply be written as 9810 newtons per meter cube. So this is simply the specific weight of pure water. So this term is known. Of course, specific gravity of the liquid is known. We can now make specific weight of that liquid subject of the formula. If we make that specific weight subject, it means that specific weight of liquid S WL is now equal to simply the specific gravity of the liquid multiplied by specific weight of water. You simply have X multiplied by specific weight of water. So this helps us to find the specific weight of the liquid. Therefore, WL is equal to X is given as 0.85. You simply have 0.85 multiplied by specific gravity of water or specific weight of water, which is 9810. And of course, if you carry out this analysis, I think you're going to obtain 8338.5 newtons per meter cube. So this gives us the value for the specific weight of that liquid. Okay, so the first aspect of the question is solved. The next aspect says find, of course, we are asked to find density as well and specific volume. So if we know specific weight, we can find density. Not forgetting, recall, we also said that specific weight of that liquid, specific weight of liquid can also be given as density times gravity. We said this earlier, that specific weight of every liquid can also be given as density times gravity. So if the question is asking us to find density, we simply make rho subject of the formula. This means that rho, which is density, is now equal to specific weight of that liquid, which we found now, divided by 9.81. That is simply gravity. That's all over G. Okay, so this is equal to the specific weight of the liquid gave us 833.8, gave us 8338.5 all over 9.81. So this simply implies that density is actually 850 kilograms per meter cube. So this becomes the density of that liquid. Next is to find specific volume. Okay, so specific volume, and we say specific volume, that's simply small v, is actually the volume of the given fluid or liquid, okay, divide by mass, of the liquid. And we also agree that this is also the inverse of density, which is simply 1 all over density of the liquid. So since we know the density of the liquid, it means we can find the specific volume of that liquid as simply 1 all over density which is 850. So 1 all over 850, and this is equal to 1.176 by 10 to the power of minus 3 in meter cube per kilogram. So that gives you the value of the specific volume. So this is how these formulas play out. They actually would correlate to one another. Density as mass over volume, specific gravity as simply specific weight of liquid, all over specific weight of the given pure water, which is constant 9.81 kilonewtons per meter cube. And of course, specific volume over mass, also 1 over density. Specific weight can also be simply okay, density times gravity, and of course this is how they play around. Let's look at another example, to solidify this example. Let's look at another example. All right, so let's consider this other problem on the board. It says a liquid has a specific gravity of 1.9. Question says determine its mass density. Okay, so we're also given x, specific gravity s. Okay, gravity S is given as 1.9, and we're asked to find the mass density. Okay, so of course, from what we've known, specific gravity S is simply the weight of the liquid all over specific weight of water, specific weight of liquid all over specific weight of water, and specific weight of water we already know is a constant value. Okay, is simply 9810 newtons per meter cube. So with this, we can be able to obtain the specific weight of the liquid. And if we make that subject, specific weight of liquid, WL, is simply specific gravity multiplied specific weight of water. So we simply have X times specific weight of water. Now, this simply means that the specific weight of that liquid is simply S, which is 1.9, multiplied by specific weight of water, and that's 9810. So this actually gives us that the specific weight of this given liquid, 1.9 multiplied 9810, will give us that simply 18639 newtons per meter cube. So this gives us the specific weight of the liquid. But then not forgetting that recall, we've always said that specific weight of every liquid is simply determined by density times gravity. So which means from this formula or from this equation, we can actually find the density of that liquid. Therefore, density of the liquid is simply specific weight of that liquid divided by gravity, specific weight of liquid all over G, and this is equal to the specific weight of liquid gave us 1869639. So we have 18639 all over G is simply 9.81, and of course the density of that liquid, rho L, is simply 19 100 kilograms per meter cube. So this gives us the density of that liquid. So that is just the basic stuff. Of course, trying to play around with these formulas, know your formulas very well. These are the basic foundation of fluid statics: density, gravity, specific weight, specific volume, and all the rest. All right, so the final thing I will talk about is simply viscosity before we can move on. So the final thing I will talk about is simply viscosity. Viscosity is another property of fluid we are going to be talking about. What is viscosity? Viscosity actually determines the friction which takes place in the layer of a fluid. It is simply the opposition or resistance that takes place against shearing action or shearing stresses in the layers of a fluid. So you see viscosity, you see it simply as the internal friction between a fluid layer or a fluid motion. So it is how viscous a fluid is that determines if the fluid can actually flow or not. That's the reason why when you pour your engine oils, you notice how thick it is, because there's a high amount of viscosity between the layers of the fluid. Same thing goes with grease. Grease also have a very high amount of viscosity, so its molecules are well bonded together because of what the intensity of viscosity that keeps them in that nature. Okay, so viscosity is simply the internal friction or the opposition to flow which takes place in every fluid. Now, the basic law that governs viscosity is simply Newton's law of dynamic viscosity. Newton's law, okay, of dynamic viscosity. All right, so this is actually the law which governs viscosity. And what is this law? Newton's law of dynamic viscosity simply states that the shear stress acting on the surface of every liquid is directly proportional to the velocity gradient of the liquid. Simply, shear stress is directly proportional to velocity gradient, simply giving us du all over dy. And of course, if I remove the proportionality sign, I always introduce a constant. So this simply implies that shear stress is actually equal to the constant here becomes mu du all over dy, okay, where tau represents the shear stress, okay, in newtons per meter squared. Of course, mu is simply the coefficient of dynamic viscosity, coefficient of dynamic viscosity, and is also measured in Newton seconds per meter squared. And of course, du over dy is simply velocity gradient. Du over dy simply means velocity gradient, which is actually expressed in per seconds. And of course, du itself is change in velocity, dy is actually change in thickness, or simply the thickness. Now let's consider a layer of a fluid flowing around a stationary boundary. Let's call this a stationary boundary, okay, and we have fluids flowing around these layers in this manner, okay. Okay, let the initial velocity of this fluid be simply u, and as it gets to this top, let the velocity change to u plus du. Let this remain the thickness of the fluid, simply dy. This is now the fluid profile, of course, flow profile, okay, and this is a solid boundary. All right, so this is actually what Newton's law is simply saying. Initial speed is u, okay, is simply u. Final speed of flow is simply u plus du. Okay, therefore, if we have this, we can now obtain change in speed. Okay, change in speed, which is simply final speed, u plus du, minus initial speed, which is simply u. So therefore, change in speed will simply give us what, du, because u minus u is off, I'm left with du, and dy is the thickness of the plate. Okay, so thickness of plate is simply dy. All right, so from Newton's law, it simply states that the shear stress acting on the layer of every fluid or the surface of every fluid is simply directly proportional to the velocity gradient. And of course, if we remove the proportionality sign, we introduce a constant, and we have this relationship for Newton's law of dynamic viscosity. Now, the coefficient of viscosity can be expressed in poise or centipoise. Mu can be in poise or centipoise. If it's in poise, when expressed in poise, okay, one poise is simply given as 10 to the power of minus 1 Newton seconds per meter squared. So if the dynamic viscosity is expressed in poise, then we'll have to virtually, of course, obviously convert to this, it becomes 10 to the power of minus 1 Newton seconds per meter squared. But if it is expressed in centipoise, okay, 1 centipoise is actually 10 to the power of minus 3 Newton seconds per meter squared. So if the dynamic viscosity is also expressed in centipoise, then of course we have to obviously convert that by using that relationship. Another way we can express the dynamic viscosity is actually to express it as a kinematic viscosity. We also have that unit, kinematic viscosity. Okay, simply symbolized by the symbol, Greek symbol, nu. This actually means nu in Greek. It's actually called Nu. That's simply nu. And kinematic viscosity is simply the ratio of dynamic viscosity to density. So simply dynamic viscosity mu all over rho. Okay, simply the ratio of dynamic viscosity to density, that gives us kinematic viscosity. So if you're given a kinematic viscosity, you might as well want to convert that to dynamic viscosity to obtain your value. And of course, from here, you can find that dynamic viscosity is simply kinematic viscosity multiplied by density. You can also obtain this value. Now, the kinematic viscosity can also be expressed in Stokes or centistokes. So when expressed in Stokes, you have your kinematic viscosity. 1 Stokes is equivalent to 10 to the power of minus 4 meter squared per second. So take note, the unit of kinematic viscosity is actually expressed in meter squared per second. So keep that in mind. Kinematic viscosity is always expressed in meter squared per second. So if the value of kinematic viscosity is given to us in Stokes, we obviously have to convert first of all by using this given value 10 to the power of minus 4 meter squared per second. If it is in centi, 1 centistokes. Okay, if it's expressed in centistokes, then 1 centistokes is simply given as 10 to the power of minus 6 meter squared per second. So that's how you convert your dynamic viscosity values. All right, guys, so I'm going to pause the video here, and in the next video, we'll start calculations involving the Newton's law of dynamic viscosity, which means we are going to be using everything we've learned here to do just that. All right, guys, I will see you in the next video. Thanks and cheers.